We'll continue with our operations research course. So welcome to this lecture. This lecture is on assignment problems. So we'll use operations research technique to look at how we can assign products to different objects, or one object A to different object B, or object I to object J. So let's look at the assignment problem. So we shall introduce what we mean by assignment problem. Then there is a way to do an assignment or to allocate resources using the Hungarian method. Then we'll look at typical world problems, or typical problems when the number of supply is different from the number of demand. So let's look at it. So usually, the assignment problem is actually a special case of the transportation problem. So if you remember in our earlier lecture, we had a look at transportation problem where we move material or product or resources from one site to a destination, right? Great. And usually when we solve the assignment problem, it's also associated with having equal number of sources and equal number of destinations. And therefore, the number of supplies and the number of destinations are supposed to be equal. They are supposed to be equal. So it has a special efficiency solution, right? And it helps us to really do a better assignment, right? So the general structure of the assignment problem is as follows, and I think we have seen this equation in the past lectures where we said that the objective function, we are trying to minimize the problem, right? Yeah, there may be a case where we want to also maximize the assignment, right? So in that case, you have to look at opportunity cost as we did in the transportation. But in this case, we are minimizing the cost of assigning one resource to another resource, right? Or one resource to a destination, or from a source to a destination. So usually it's the coefficient of the the assignment, that is the cost in transporting or in assigning or in allocating the resource, and the number of resource that is available, right? And usually we say that the number of sources, right, will be equal to 1, or the number of assignment will be equal to 1, and number of destination will also be equal to 1. So assignment is either 1 or 0. Either we are assigning or we are not assigned. So the formulation is a standard transportation problem with n sources and with m sources and n destinations, right? So where the sources Si is equal to 1, that's one particular source, and also the destination, the demand is usually 1. All right. So we'll look at the Hungarian method of solving the assignment problem. So the Hungarian method is a special solution method for the assignment problem, right? And it was developed by a Hungarian mathematician called Konik on the basis of a mathematical property, right? So the method is based on the assumption that the assignment costs, which is the Cij, right? They are always non-negative, right? They are always non-negatives, and the solution procedure will be presented here. So let's take this. So this is the process. We say that you should develop an opportunity cost table. So as soon as you identify the problem, which comes with cost, then you develop an opportunity cost table where you develop it for a row and you repeat it for a column, right? And you do that by subtracting the least value in each row. And when that is done, then you now subtract the least value in each column. Any other direction or any other way you do it is always arise at the final or the optimal answer. Yeah. So there's no wrong answer or no wrong direction, right? Then when that is done, we draw the minimum number of horizontal or vertical lines necessary to cross out all the zeros, right? We start with the largest or the number of zeros in each column or row. Then we see if all of them have been crossed, that is M is equal to N, is satisfied, that the number of sources is equal to the number of demands, right? If that is not, then we go to 3, that is we subtract the minimum uncrossed value from all uncrossed value or uncrossed cell, and then add the same amount to all the values at the cross section of the line, right? So when that is done, then we test the M is equal to N unique and see if that is satisfied, then an optimal solution is achieved. So we'll demonstrate with an example, and therefore we'll go to whiteboard and we'll do that demonstration from there. All right, so let's move to our whiteboard real quick. So we'll take this as an example. So this is an example of assigning an operator to a machine, operator I, to a machine J, right? And the number of assignments, the cost. So the cost of assignment is from 1 to 1 is 7, from 1 to machine 2 is 3, from 1 to machine 3 is $5, from operator 2, if you assign operator 2 to machine 1 is 8, or you assign operator 2 to machine 2 is 9, in that order, right? However, one assignment can only be done, right? And one machine needs one machine, right? Or each machine needs one operator. And therefore, we can see that the number of demands and the number of supply for each machine amounts to 1. So what is Connect saying about this, the Hungarian method? So it says that you first have to cross out. So let's bring another table here, right? Let's say that this leads to this table real quick, right? And let's have our 1, 2, 3 machines, operators. So operator, let me use I. Then let's have our supply here. Let me use J, 1, 2, 3 machines. Then we need 1, 1, 1 here, right? And the maximum is that. So it says that we should subtract create an opportunity cost table. So I will do with the row first, right? You can also start with the column. Any direction you take, we should all arrive by the same answer. So I'm subtracting the minimum value 3 from each parameter, each cost. So 3 from 7 will be 4. 3 from itself is 0. 3 from 5 is 2. Then we'll also have 2 from 8 is 6. 2 from 9 is 7. 2 from 2 itself is 0. 6 is the minimum. 6 from 9 is 3. 6 from itself, 0. 6 from 8 is 2. All right, so this is the row reduction, right? This is a row reduction. So this will again give us, lead us to the next opportunity table, right? The next opportunity table where we create another column reduction, right? We create a column reduction for the next reduction table. All right, so the column reduction, again, within this column, the first column, we have 4, 6, 3. The minimum is 3. So we subtract 3 from all the values in the column, and we have 1. 3, 6 from 6, 3 from 6, we have 3. 3 from itself is 0. We have 0, 7, 0. So the minimum is 0. 0 from itself, 0. 0 from 7, 0. 0 from itself is 0. Then 2, 0, 2. 0 is the minimum, so 0 from 2 is 2, 0 from 0 is 0, 0 from 2 is 2. All right, so when we have this, then, so we've done our row reduction, and we've also done our column reduction. All right, so what the Hungarian method says is that then at this point, we cancel the zeros out. So we'll start from the number of zeros. So on the first row, we have 1, second row, 2, third row, we have 2. So we'll cancel this first. We'll cancel this first. Then we'll look at, we'll cancel this first. Yeah. Then we'll look at the next number of zeros here. So 1, 1 in each row. So you can either go horizontal, you can go clockwise. Yeah, horizontal or vertical, right? So let's assume I'm going vertical here and I'm going horizontal here, right? So how many lines have I achieved so far? 3. So 3 is equivalent to m is equal to n. Because m is equal to n is 3, right? Then it means that the solution is optimal, right? So how then do you allocate your resources or your operators to the machine? Or how then do you do the assignment? So you see that when you come to the one with the list 0, you start from that. So you can see that I can allocate, so let's say I have operator and I have machine. So I'm putting operator I, machine J. So I'm saying I have operator 1. I'm assigning it to machine 2, right? And what is the cost? So operator 1, machine 2. So I can say this. Okay, there's no need to do those lines, right? It's not necessary. So machine 1, operator 1 to machine 2, operator 2 to machine operator 2 to machine 3, and then I can assign operator 3 to machine 1. So if that is done, what's the cost for 1, 2? 1, 2 is 3, 2, 3. So from this table, we read the cost, right? The original table. 2, 3 is 2, then 3, 1 is 9. So the total cost here is 9, 11, and 9, 3, 9, 3, 2, 9, and that is 14. So the total cost of assignment is 14. And this is how the assignment problem works. Very easy, very simple, right? Great. So let's take another example and let's see how we can assign this. All right. So from this problem, right, we may in fact look at the whole thing and say, okay, why don't I assign machine 1 to operator 1? Why don't I assign operator 2 to that? Why don't I assign that? And why don't I assign this? Oh, okay. Perhaps it's better to do this way and then this way. Okay, so I think the red one is the best. And then we'll just say, okay, we've done the assignment. But this is not how the Hungarian method says. So it says that we should use the row reduction and we should also use the column reduction to do this. So let's see the row reduction. Yeah, and as I said, any direction that you take will arrive at the same solution, will arrive at the same solution. All right, so let's see the row reduction. So for the first row, the minimum is 10. We subtract from all the values here, and we're going to have 0, 5, 6, 8. The second row, the minimum is 10. We're going to have 4, 360. The third row, the minimum is 8. So you're going to have 3, 1, 0, and 10. Then the fourth row, the minimum is 9. Going to have 4, 4, 2, and 0. So here, after this, then we do the column reduction. So we do the column reduction here, right? So with the column reduction, let's still have 1, 2, 3, 4 machines. 1, 2, 3, 4 equipment operators. Yeah, operators. So the column if is 0 is the minimum. So 0, 4, 3, 4. The minimum here is 1. So 4, 2, 1 from itself 0. Then 1 from 4 is 3. Minimum is 0, so 6, 6, 0, 2. Minimum is 0, 8, 0, 10, 0. All right, so after doing the row and the column reduction, then we see how we can do our allocations by crossing the zeros. So the maximum number of zeros I have is 2, right? So I have 2 in the row, so I have 2 here. I cross them out first. Then I also have 2 in this column. I cross it out. Then I have row, only 1 in the, I can go vertical or horizontal. Yeah, so when this is done, then we see how many lines did we get? 3. However, 3 is less than m, which is equal to n, which is equal to 4. So since 3 is less than 4, it means that the solution is not optimal. So how then do we do the next optimization or the next reduction or the next iteration, right? So with the next iteration, we have to find the minimum on cross value. Yeah, the minimum on cross value and subtract from all the uncross values. Then at any intersection, we add that minimum value to that cross section or the cross where the lines crosses itself, right? So if we are to do that, then we are going to achieve. So let's draw our next tableau here. Let's draw our next tableau here. So I have 1, 2, 3, 4 operators, 1, 2, 3, 4 machines. So actually subtract the minimum I have here is 2, right? So I subtract 2 from all the uncrossed. So 2 from this already 0. 2 from 4 is 2. 2 from 6 is 4. 8 is already crossed. 4 is already crossed. 2 from 2 is 0. 2 from 6 is 4. 0 is already crossed. 3 is an intersection. So we add 2 to it, which is 5. 0 is already crossed. 0 is already crossed. 10 is an intersection. So we add 2 to it. 3, 4 is already crossed. 3, 2 from 3 is 1. 2 from itself that. And 0 is already crossed. All right, so here, after that, then we do the crossing. So how many zeros do we have in the first row? 1. In the second row, 2. Third row, 2. Fourth row, 2. What about the column? First column, 1. Second column, 2. Third column, 2. So the maximum is 2. So it means that we can cross 2 first, 2 second, 2 third. Then we have 2. So number of lines crossed is 4. And 4 is equal to m, which is equal to n, which also is equal to 4. Therefore, the solution is optimal, right? So if it is optimal, then what is the assignment? The assignment is this. Okay, let's say we have operator, right? And we have machine, then we have the cost. So operator, machine, cost. So operator 1, operator 2, operator 3, then operator 4. All right, so 1 will be assigned to 1 because you can see that. So when you are doing that assignment, you go for the least zeros first. So 1 to 1 is 1 machine, right? And 2 can be assigned to 2 or it can be assigned to 4. So let's say I'm assigning to 2 first. 3, we can go this way, 2, 4, right? Later on we'll make it, we'll clean it up. 3 can be assigned to 2 and can also be assigned to 3. Then 4 can be assigned to 3 and can also be assigned to 4. So it means that if we are to clean it, then we can say that let's assign 2 to 2, let's assign 3 to 3, and let's assign 4 to 4, right? So in that case, we have 2, 3, 4. So we have 2, 3, 4. Now from the original problem, assigning 1 to 1 is 10. Assigning 2 to 2 is 13. Assigning 3 to 3 is 8. And assigning 4 to 4 is 9. So the total cost here will be 40, right? It will be 40. Yeah, we also have an alternate assignment, right? Alternate assignment. So with the alternate assignment, right? With the alternate assignments, yeah, we'll see that 1 can still be assigned to 1, right? And 2 could be assigned to 4. 3 could be assigned to 2. Then 4 can be assigned to 3, right? So what is the respective cost here? So the cost here, when you look at the cost from the original table, 1 to 1 is 10, 2 to 4 is also 10, 3 to 2 is 9, then 4 to 3 is 11. Again, if you sum this, you should get 40. Yes. And that means that we have still achieved an optimal solution. All right. So in this case, you would realize that the solution actually has optimal solutions, right? So we have multiple solutions here, right? Okay, so let's take another example where we have unequal number of um, equipments matching operators. So that total number of supply is not equal to total number of demand. Let's look at that example. So this is a typical problem where we have 4 operators and 3 machines. So the number of operators is 4 and the number of machines is 3, right? So you see that this is unbalanced. So there is an unequal number of supply demand problem. So what we do here is to balance the problem, right? So for us to balance the problem, so we have to create another column, and put all the, make sure that it is balanced. So this is what we do. So we have from I to J assignment 1, 2, 3, 4, right? Then 1, 2, 3. Another column, which is a dummy, right? Which is a dummy. So the cost will be 7, 10, 4, but the dummy allocation is 0. 9, 8, 6, the dummy allocation is 0. 11, 3, 2, the dummy allocation is 0. 7, 6, 3, the dummy allocation is 0. Now, after doing this, then we'll go back to our row reduction and our column reduction. So if we go to our row reduction, let's say I'm doing row reduction, right? Okay, let me do column reduction because in our previous examples, I've always started with row reduction. So if I'm to do column reduction first, right? So I'll arrive at this. So I have my 1, 2, 3, 4 operators. 1, 2, 3, 4, which is a dummy machine. So from one operator, it's assigning it to a dummy. So the row reduction, no, column reduction first, we are saying that we should subtract the zeros from all. So I pick the 0 here and I subtract from every value, and that will be 0. So that's what I do first, right? Because it's easy, right? And the next one is to look at the next column is 2. So I subtract 2 from 4 and I have 2. 2 from 6 is 4. 2 from 2 is 0. 2 from 3 is 1. Then I look at column, the next 3. 3 from 10 is 7. 3 from 8 is 5. 3 from itself is 0. 3 from 6 is 3. Then I look at the next column, which is column 1. The minimum value is 7. 7 from itself is 0. 7 from 9, 2. 7 from 11 is 4. 7 from 7 is 0. All right, so after this, then I will do my column. After the column reduction, then we'll do the row reduction. All right, so the row reduction here. So I want to have my next table here. Yeah, just making sure that everything is sequential. So have that from I operator to J machine. 1, 2, 3, 4 operators. 1, 2, 3, 4 machines, but the fourth one is a dummy. I'm just putting it here to remind myself. So when I do the row reduction, right, the number of so is 0, so 0, 7, 2, 0. So I have 0 here, so 0, 4, 5, 2, right? So it's just the same thing, 4, 0, 0, 0, then 0, 3, 1, 0. So the row reduction leads us to the same column reduction, right? So then how do we cross out? So your first cross out the maximum number of numbers in the column, right? So here, for the first row, I have only 2. The second row, I have 1. The third row, I have 3. And the fourth row, I have 2. What about the column? The first column, I have 2. Second column, I have 1. The third column, I have 1. And the fourth column, I have 4. So I'll cross out the 4 first because that's the largest number of zeros in the system, right? So now I'll reduce the table to 1 row, 1 0 in the first row, no 0 in the second row, 2 zeros in the third row, and 1 0 in the fourth row. When I look at the column, 2 zeros in the first column, 1 0 in the second, 1 in the third. So why don't I continue with column crosses? So I cancel that. The next ones are all 1 1s, right? So I go that. So 1 0s, 1 0s. I go that and I have that. So I have 4 number of crosses, right? And this 4 is equal to M number of operators, n number of machines, which equal to 4, and therefore the solution is optimal, right? So if the solution is optimal, how do I allocate, or how do I do my assignment? So the assignment is achieved as this. So operator I, machine J, then costs. So we can have that and say operator 1, operator 2, operator 3, and operator 4. So operator 1, so we say we go with the list zeros for a particular row or column. So for a particular column, when you look at the number of columns here, for the first column, I have 1:1 and 1:4. So I can see that 1 is assigned to 1 or 4. The second one, 2 is only assigned to 4. 3 is assigned to 2, 3, 4. Then 4 should be assigned to 1 or 4. All right, so we can see that 4 can only be assigned to 2, right? 4 can only be assigned to 2. So it means that this 4 cannot exist, but it can only exist for the 2. All right, then 1. 1 can only be assigned to 1. So it means that 1 can only be assigned to 1, and 4 can also be assigned to 1. So I have 1 here, I have 1 here. So I have 3, which can be assigned to 2 or can be assigned to 3. So what we'll do here is, remember 1 is a dummy, so it means that one operator is idle or cannot be assigned, right? One operator cannot be assigned. So it means that let's decide to assign 1 to 1, right? And let's say that 4 is assigned to 4 is left out, right? Okay, so let's see if the reductions we did it. I think there is a problem here. Yes, I think there is a problem here. So our row reduction, we might have missed it. We might have missed it, and this is how you see, because you see when you can't assign 1 to 4, because when you assign 1 to 1 and 4 cannot be assigned, right? We can't say 4 should never be assigned to what? It needs to be assigned to a machine. So we have missed it. Let's see our row reduction table. Let's see this table again. All right, so in canceling this table, right, we cancel, let's use a different color. So we cancel this, 1, 2, 3, 4. The next one is 2. We cancel this. The next one should be row, should be this. We should cancel this. So the number of cancellations using the green will be 3, which is less than m, is equal to n, is equal to 4. So one more iteration is needed here. All right, one more iteration is needed here. So that's the error here. So if we don't follow the Hungarian method, we are going to miss it. So let's do this reduction again. All right, so we have this reduction. We'll still leave the red markers inside, just so we know that if we are not careful, as I always say, operation research will try to train you as engineers to be careful. All right, so let's do the next iteration. So in the next iteration, right, which is this table, we are again assigning I operators to a machine, and we have 4 operators. And we have 4 machines, but the 4th one is a dummy machine, right? So the rule here is that, so here we have not canceled these zeros, right? So the rule here is that what is the minimum? The lowest number here is 1. So it says that you should then subtract 1 from all the uncrossed values, right? So let me count, 1 from all the uncrossed values. Okay, so 1, 0 is already crossed. 1 from 7 is 6. 1 from 2 is 1. 1 from 0 is already crossed. 1 from 2 is already crossed. 1 from 5 is 4. 1 from 4 is 3. 1 from 0, 0 is already crossed. 1 from 4, so because the crossing are meeting here, so we add. So that means 1 plus 4. 0 is already crossed. 0 here is already crossed. So we also add 1 here because 0, which is intersection between the crosses or the 2 cross lines. Now, 0 is already crossed. 3 minus 1 is 2. Then 1 minus 1 is 0. Then we also have 0. All right, so here we do the crossing again. We have 3, 1, 2, 1, 2 in this row, 3 in this column, row 3, column 2, 2, 2. So I can go column, which is 3. I have 2. I have 2. Then I have 1. All right. So now how many crosses do we have? 4. 4 is equal to m, is equal to n, which is equal to 4. And therefore the solution is optimal. All right, so we do our allocation again. We'll come back to this tableau or this table that we created here. And we will see. So 1 from here, 1 can be assigned to 1 or 4. 2 can be assigned to 4. 3 can be assigned to 2 or 3. 4 can be assigned to 1 or 3 or 4. All right, so now 4 can only be assigned to 2. Therefore, 4 cannot be assigned to 4 cannot be assigned to 1. So let me cross it out like that. And 4 can also not be assigned to 4. All right, so 1 is assigned to 1. Only 1 cannot be assigned to 4. So I'll take it out. Right? 3 is assigned to 4. So because 3 is the only one left here. So 3 cannot be assigned to 2. 3 cannot be assigned to 2. So therefore, the correct assignment here will be 1, 4, 2, and 3. So I can clean all this and make the assignment work, which is 1, 4, 2, and 3. Okay, so what this means is that we assign 1 to 1, 2 to 4, 3 to 2, and 4 to 3. So we go back to our original problem and we'll see the associated costs. So 1 to 1 is actually 7, right? 2 to 4 is a dummy, so 0. So it means that we do not assign to the operator. Yeah, do not assign him to any machine. 3 is assigned to 2, and the cost is 3. 4 is assigned to 3, and the cost is also 3. So the total cost here will be 7, 10, 13. Yeah, it will be 13. All right. So you see, if you don't follow the Hungarian method very well, you are not going to have the assignment, right? You are not going to have a correct assignment. So many times there's an issue, go back and check and see where you have missed it. All right, so that is the end of the assignment lecture. Thank you very much for being with me, and we'll meet in the next lecture. Cheers. Bye.